we should get right to it. We have a lot of stuff to cover. Let me attempt to bring you back before I bring you forward. Let me just bring you back a step or two. What we were doing is we began by thinking of a function of phi. I'm going to keep that notation here. Phi goes from 1 to 0, 0 to 1. And we did that because we want to inherently think about a period of a certain length, but I didn't want to really worry about the actual length just yet. So I like to write in terms of these normalized variables. And so then phi became its own thing. The unit rate at which you turn around the cycle, that's phi. Then we talked about space and time, period, big T, wavelength, lambda, spatial frequency, temporal frequency, they're inverses. And then if you take it into account as a radians, so there's a 2 pi again, then you're in omega, angular frequency, and spatial wave number, often K. The notation, as will your mileage, will vary. I then sort of pulled out two facts known about sines and cosines. One, of course, they are together defining an exponential. And so you'll also see these cosines equals e to the I plus and e to the I minus and so on. And then the fact that the sum and square, then they add up to 1, and all of that trigonometry, which I suppose you know. And by suppose, I mean I expect. And by expect, I kind of mean that you're required. So then the next thing is you want to integrate a function of a cosine and a sine to find its average. Well, that's 0. So you want to multiply two functions together. Then you find out that if you multiply the same or different functions, that they are giving you something or nothing. So that's the beginning of orthogonality. I did that, but I also already then inserted a rate, right? The rate at which this function now turns around the sphere, the rate of cycling, right? And so on more rapidly. So that is the notion of having more wiggles on that unit interval. That gives you the notion of integer times full wavelengths that fit inside somewhere. Okay, no notion of anything happening outside of this interval. I want to fit things in it. So if you want to think about waves on a string, that's what it is. An organ pipe that you close on both ends. That's where these things come in. And then you notice again, it's 1 or 0. And if you properly normalize it, you get literally 1 or 0 as opposed to some other number, which would be enough for orthogonality. But orthonormality implies oneness, unity. I then rewrote that for here. This is not hard to do. Thus, you can verify it. That's the sort of a thing to remember. What that means is that you take the set of these functions, cosines of 2 pi n phi's and sines and so on, including 1, which is the 0 frequency one, and that is a basis. What do we mean by a basis? It's a basis for space. It's a space that contains functions. What kind of functions? Functions that are square integrable, that if you take their square, absolute value square, and integrate them on that interval, that you don't end up with infinity, which would be a sad, sad function. And so any function, hyperbolic arctangent, log, or whatever, if it satisfies these requirements, which I'm now not checking about those two examples, is expressible as a linear combination of elements from this basis of this function space. Cosines and sines, this is going to be good for a real valued function that have finite energy, even though I suppose you could say, well, how about I multiply it by I and then I get a complex function? Fine, be my guest. Don't overthink it. All right. So notion of a basis, linear combinations give us, and then I'll hit the focus button again just to be sure. So then I wrote this equation, which was too long for the screen. So I'll angle it. There will be a function little s of phi. I know it will be a linear combination of these basis functions. How do I interpret that? Well, I take the first one, that's 1 times a constant, that's a0. Then I take a bunch of cosines and sines with the n phi's and the 2 pi's. I'm multiplying by numbers, a sub m, b sub m, and I sum them over all the m's that I can think of to some upper limit big M. I claim that's a representation of the function, but you know that this basis has many, many more terms. I just selected the first m. So that's an m-term approximation of this function. And when I compare it to the real function, in the mean squared error, in our traditional way of looking at things, a big phi would have been called that. The misfit that we've always been dealing with in linear inverse problems has always been that, except we have had this discretely. This would have been a big phi. Another notation would have been S of little phi. There are only so many letters. So this is little phi, it's a black phi. Mine is this approximation, which I'll just call S hat for a new notation. I'm not telling you anything new, I'm just rewriting it in a new notation with m terms, or m plus 1 terms, I don't want to think about it. Still a function of phi, a little phi, right? And other ways in which I have notated this sort of stuff is by saying, well, that could be a 2-2 norm, right? I might as well save that m in here. So if I want to think about this discretized, then every value, absolute valued and squared, and then integrated, which really means summed times an interval, that's the same as, you know, thinking of a discrete vector and saying x dot x, and that was always the length of that squared. So that's our mean squared error, as usual, except it's continuous now. And then the assertion is that in the limit, if I up the number of terms and I keep going, that I can reduce this mean square error to 0. So no pointwise convergence, but mean squared convergence. And so from now on, that led me to say, well, if I'm going to write MS, that's the definition of is here is a mean squared sense. Then I write this thing as an infinite Fourier series, hereby defined for signals that are square integrable and that live on this interval 0 to 1. Done. Sole condition, as usual, we're going to have this thing here, the fact that when you generate or when you integrate the signal that you're trying to deal with and squared integrate it, so the mean square value of the signal itself, that be finite, okay? More notation, remember this phi, that's an L2, remember that was a little L2. That's a sort of the jargon for the L2 norm, little L2, that's slash ELL in LaTeX. The sort of signal space that is square integrable, that's called big L2. That's more jargon than you need, but you will find it. It opens up a whole library of other books when you deal with function spaces. And then they'll go, oh, I'm in L2, right? And you're like, yeah, but is it little or small or big L? Anyway, so L2 is a so-called Hilbert space of signals that have finite energy. And so you define what it means to be a norm. You define what it means to be integrable, and then you're busy doing it. So for these signals, which are what you and I know to be of relevance, you know, the temperature in the room, chemical concentration in your backyard of some pollutant, whatever it is that you'll be doing, is going to be L2, more likely than not, until it isn't. That'll be fine then to represent by a finite set of terms in a Fourier series. I ran out of time, I suppose, and I was going to just write some thoughts here to re-establish myself. The big reason why do we do this? Well, here is an example, right, of why are sines and cosines so important. This is a temperature record outside of GEO Hall, right? You don't even need to see it clearly. Squint at it and you see it goes up and down, right? Whoever came up with the concept of sines and cosines in probably Sumerian, Babylonian times had already figured this out, right? The Earth is round, they knew it then. The Earth is rotating, they knew that then. And not any fool, but you know, it didn't take much work for them to figure out that if you shine a beam from a great distance at something and it casts a shadow, that the length of those things, defines the function sinus and cosinus. And so it is just natural. I'm going to cut it out here and stick it on here. We're always thinking first of sines and cosines because they're everywhere and we live on Earth. That's my geo motivation. And I know that the daily temperature in Geo Hall, outside, is influenced by this rising and setting of the sun on a 24-hour cycle. And if you keep track longer, that you'll find a 182.5-day cycle and a 365.25 cycle. And then if you're doing longer and longer intervals of time, you will find more and more cycles because, on our planetary scale, there is a lot of stuff turning around a lot of other stuff. Okay, Earth science trivia question. The cycles in Earth's temperature. Here I'm telling you, there's the daily cycle, also known as the diurnal, SAT word for daily. There is the seasonal cycle, right? If you go longer and longer in time, and I don't need a full dictionary, but what other cycles are there in the Earth's temperature?
Orbital cycles, like precession, eccentricity, obliquity.
Okay, great. And then order them for me.
Precession is like 20,000 years. Obliquity is like 41,000 years. And eccentricity is 120,000 years or 100,000 years.
Okay, so something like that. 24 hours, 365 days, 18 to 23 kilo year, 40-ish, 100-ish, and then you have combinations that multiply them into even longer ones. But so yeah, vital cycles, the way the Earth's axis tilts more and more, precesses around with that tilt, and then how the Earth's orbit around the sun gets more or less oblique. It is not an Earth science class at this point. You should all know what causes the seasons. Well, you should, period. You should all know what causes the seasons. I'm saying that because there is this familiar science education YouTube video that asked this question of the 1999 graduating class at Harvard. And yeah, they all got their diplomas, and what, like a quarter of them actually knows what causes your seasons. And it shows you both that your diploma ain't worth nothing, and you don't actually need to know this stuff. Okay, you can go around the world and about your day without truly knowing what the seasons are, but clearly that is not our standard of inquiry. Anyway, that's my motivation for signs are important because they're everywhere, because we're round and rotating. There is no need for that. That's not the only representation, okay? There are other ways, including one that we've already done. We've already approximated signals on an interval using polynomial basis functions. That whole business with, oh, it'll be ax plus b or plus bc x squared. Those are polynomials. That's a signal basis, not necessarily orthogonal, but it's something that one can work with. Certainly convenient. Didn't tell you the signs are the best, although I'm saying that for these things they're going to be really good. So we're stuck with that. I wanted to say, well, how to find the expansion coefficient. That's my definition now for a basis expansion. That's the jargon. AM and BM are expansion coefficients, basis coefficients, Fourier coefficients, Fourier series coefficients, all synonyms. And clearly our objective is, this is a linear model. This is a linear model for the signal. We're trying to find a mean squared representation that best fits. So you already know how to solve this. If you discretize it and wrote GT, G inverse GT, that would be right back to what I'm going to say, because we've done that, and I'll make the connection again later. How to find the expansion coefficients quickly, written, you discretize, and you do the M1 inverse, as I've been calling it, the overdetermined inverse. I'm not going to work this out, but I want to have set it, okay? And I want to remind you then, right, that this is about GTG. All those times we talked about GTG, GT dot D inverse as the solution for an inverse problem. Nothing new, the same old thing. I want you to see that G is going to be filled with ones, and then sines, and then cosines, and then sines of another frequency and cosines of another frequency. Every column is going to represent a different cycle. You can write this already. That's why I'm not writing it here. So same way you fit a quadratic, you could fit a sine or a cosine of any number of terms that you want. Perhaps I'll write down the name of my little function I have on my GitHub, which is called, what is it now called? Period fit, I believe. Okay, where you can try these things as linear inversions. We've already done that. I also want you to see, imagine this here, this GTG. So now I need your mental, I need you to picture a tall matrix with lots and lots of data points, time points down the rows. And the first column of it is 1. And the second one is, cosine phi. And the third column is sine phi. And the fourth column is cosine 2 phi, and then 3 phi, and so on. And then I want you to mentally transpose that matrix. And then I want you to mentally multiply that matrix by itself. What are you then doing by any other words? If G is a discretized Fourier series coefficient matrix, then it contains ones and sines and cosines at all those phi's that you have, all those times that you have down the road. And when you flip it on its side and you multiply it by itself, what are you doing? What are you doing? How can I ask it in any other way than what are you doing? By another word as for that operation. Let me write, I didn't want to belabor, but now I will, right? So here is sine m phi for whatever m. And I have a million such points. Let's say let's phi go from 1 to 0 to 1. I'm writing it as ugly as I can. Okay, that's my G. That's a column of my G. So now my question is, if I do G transpose G, what am I really doing? Well, what am I really doing? Then I'm taking sine m phi 1 times sine m phi 1 plus sine m phi 2 times sine m phi 3, and so on, right? Imagine this as a row vector now. I'm doing the matrix product. I'm writing it underneath here. This times that plus this times that plus this times that plus this times that. I'm writing all these terms. If phi 1, 2, 3, 4, 5 is just a discretized time axis or space axis, then I want you to see that this is proportional to the integral of sine m phi times sine m phi over phi, because the integral is like the sum, never mind the interval. So this thing is a discretized form of an integral. And since I've been telling you that if you do this integral for different m's and n's, it ends up in nowhere, nothing. But if you're doing it for the same function, cosine sine, of the same frequency m, you end up with a 1, properly normalized. So I want you to immediately see that GTG, if you give it the full interval, is a product integral that's going to give you ones on the diagonal and zeros outside. And then you invert that, it isn't at play, because the inversion of an identity matrix is just 1. So I'm not making that argument formally and longly, but if you've got the complete interval really well discretized, this first term is not even there. because this amounts to an integral of something whose answers you know because you can do it by hand, and its inverse is immaterial. And so you're left with the solution, which is GTD, which again is an integral. It's an integral of the sines and the cosines with the data vector. And that GTD, which is left, I want you to see that in your mental head, in your head mentally, your mental picture of that should be that's a discretized form of a sine function over the entire interval times your data. And if you want to think about that as a correlation integral, you'd be fine because that's also what it is. You're asking, give me my data sequence, multiply them by a sine of a certain frequency, dot-wise, point-wise, integrate it out, which is equivalent to a sum, and then tell me if that's a big number or a small number. So that's another way of saying that the Fourier coefficients that come out are like little correlation coefficients of the target basis functions with the data. Correlations of the basis functions with the data. And so if I look at my temperature series and I try, if I literally say I'm going to superimpose a 12-hour cycle on this thing, and then I take the product of that with my actual data and I sum and integrate it, I'm going to have very little correlation there. That's going to show me almost nothing because that term isn't at play. But if I offer a nice sinusoidal cycle of a 24-hour period, all I got to do is adjust the height of it and perhaps move it into phase, and I will pull out a nicely correlated set of that. And that's all contained in here. Again, I'm not giving you the full lecture on that, but I want to put it all here that's all the same thing in a new form. So the second bullet point here is that something that you probably learn elsewhere when you're doing orthogonal functions is to say, well, all right, if you have this integral orthogonality from before, and you have this series representation from before, and you want to find these unknown coefficients, the classic trick that they teach you in some classes, no doubt, is to say, multiply the left by a cosine of some n phi, and the right by a cosine of n phi, and integrate it, because it will only pull out the term of the appropriate cosine, sine, or frequency if it's the right one. Integration kills all the other ones. That's how you peel out individual coefficients. So I'm going to just write this here and say, integrate against a target function, and orthogonality does the rest. So that's the real answer to continuous variable Fourier series. How do I find the coefficients? You integrate against a target sine or cosine function. And if it indeed is a sum of sines and cosine, then the orthogonality will integrate all the terms that aren't the target and leave the one that you want, and that's going to give you the coefficient. So many textbooks, including the ones I recommend you read, will talk about that and they say, oh, that's how we find the Fourier series of a boxcar or a triangle function or whatever the popular examples are, and they give you analytical forms for these integrals and say, here is the Fourier coefficient of this or of that, and that's because they hand integrate, cross multiply, and orthogonality gives you the coefficient. And I began with the previous thing because we have been doing that, and I make several steps here, but I'm saying, well, what is integrating against? Integrating against, I mean, multiply the data vector by the target function and then integrate the product. Well, that's like doing this, GTG, if your GT is indeed filled with those target functions, which it is. And that is what you would have gotten if you just tried to do an inverse as a regular old inverse, the way we've always done it, knowing that because you have orthogonal functions on the interval, that GTG inverse matrix isn't there because of orthogonality. So I'm linking here continuous orthogonal function integration with a discretized version of it with the overdetermined inverse, with all of that baggage that comes with it, to put you into familiar territory in the sense that this is nothing new. Okay, and I've thrown the word correlation here because correlation is nothing else but an integral or an expectation or a sum of product pairs, and so that's where the statistics are going to come back. So the words here are correlations, integrating against, orthogonality being everywhere, discretization, all of these things, they're going to make sense even more and more. I wasn't going to go into that much detail, and now I didn't actually go into that much detail, but is that beginning to make sense? Sort of a cautious yes would be in order here. You asked about the meaning of this A0 term, and like that's like the mean, right? And I want you to think about this and say, well, what does it mean to integrate a function around against 1? That's called taking the mean, right? Remember the A0? That's like saying S of phi times 1 d phi over 0 to 1. I'm writing really small here, but I'm just saying it in words, right? The cosine of 0 frequency is the 1 function, and you integrate it against. That's the same as saying integrate the function, which is the same as saying proportional to saying take the mean. That's why that is the 0 frequency is the signal mean. And which again connects to what we've always been doing, because if I say it's a polynomial representation of 1 term, then it is, again, I did that for you, the GTG, of ones, it is 1 over m times the sum of the data. And so all these things are one and the same thing. But we do need a bunch more because we're not seeing half of it if we don't progress from this. Okay, so what we have been now defining is a Fourier series, and it has been continuous time and discrete frequency. Whatever I've written phi as a continuous variable, and I've written this result as a sum over specific terms, discrete frequencies, m, 1f, 2, 3, 4, 5, okay? And I've written it for real valued signals, and I've written it for sines and cosines. I'm just going to now write it again, but I'll write it as a single sum that says discrete frequencies. Yes, sir. How many? Well, an infinite amount. I'm going to say S wiggle of m is my Fourier coefficient. And I'm going to use my I2 pi m phi notation to say, well, that is a representation of the signal in the mean squared sense for that interval going from 0 to 1. I'm going to close it. Okay, so that's the same thing as before, except in continuous functions, because I no longer draw 1 cosine m phi and sine phi, but I draw e to the I2 pi m phi. And if m is 0, that function is 1. So then I rewrite and I say, now my new definition is S wiggle of the discrete m is given by, now remember, I gave you the integral orthogonality if I left multiply by e to the I2 pi n phi and right multiply it and integrate. Orthogonality kills that term. I pull out this coefficient, and the result is that 0 to 1 of S of phi times the target, complex conjugate as it may be, negative I2 pi n phi d phi. And that is, for all m natural numbers. I always forget what that's called. All right, so this is a Fourier pair, and it's a restatement of what we've been having. Okay, you all do want to leave the unit interval. And so if I go back to, I'll just say it so you can go back later to the beginning. I'm like, remember, we were talking about phi being the proportion of t over a big T, some sort of a period. I just want to start thinking about that period as my interval. And that's because I'm going to want that period to take any value, including really, really large. And so now I'll just draw an interval that goes from half t negative to plus t. And now I'm thinking of a cosine and a sine that, you know, fits in here with a particular frequency. I'm not drawing so well today. All right, so just some examples of some functions. And so I just want to rewrite this Fourier pair as f of a variable t, little t. I'm just going to sort of copy it. You'll see it's not fundamentally changed, where this goes from negative infinity to plus infinity. And I will have my s wiggle of n, and I will have my e to the I 2 pi of n. Now I call it f of n, f sub n times the time variable, whereby, in other words, my f sub n is my frequency, right? These things are now called frequencies. And if you want to think about them as index m divided by that period t, well, that's exactly what it is. I'm just rewriting it. And the spacing of these frequencies, which are called delta f, is 1 over t, because I have 1 over t, 2 over t, 3 over t. And so then I want to say that my discrete frequency Fourier coefficient, S of n, is, now I divide by the interval. We didn't see that division earlier. I go from half t, big T, to full t, or, well, plus t over half. I write my I to the negative I 2 pi. I write my frequencies. I write my time, and I integrate over time. D phi as t over big T. So here's my t. So same thing, equivalent thing, a pair that tells us what's going on. So now the mental gymnastics that we need to do is we need to let go of this special interval of length big T and go to a Fourier integral transform. And I'm going to call that the continuous time, continuous frequency version of it. And I'm going to write it, and I'm going to tell you why that should make sense. There is some mental gymnastics involved in getting to this point, but if you let t go to infinity, your delta f, the spacing, goes to, you know, nothing, very small, differentially small. So that's sort of like little df. And if you maintain integrability and so on, then you can let time go to infinity and let this interval stretch out to infinity. And then you arrive at a signal representation that I'll begin writing here as s wiggle. The wiggle is the transform variable. And now it's of a continuous frequency, f. And that is going to be the integral over all of time of whatever you have times any and all of these frequencies no longer indexed by n, but now continuous variables, t dt. So that's the equivalent of here, when the step between here and here is to say, let go of a period t that you need to fit your cycles in exactly an integer number of times, which I'm not drawing well here, I realize. But let t go to infinity, as in anything goes. The signal no longer has to be periodic, but it continues on to infinity. And then your delta f goes to 0, but really that's really a df integration variable. And your df was 1 over t anyway, so that disappears. And if you do the derivation a little bit more properly, it's not that long, but then you end up with no longer having a sum over discrete frequencies like in the second pair, but you also have an integral over continuous frequencies of that now integral transformed of the function with the continuous argument, and then e to the I 2 pi of that continuous frequency times time over df, or rather against df.
We can't really see all that. It's kind of hidden by your border.
The border says time goes to infinity, big delta f goes to 0, which is differential f, integrate, the sum turns to an integral. And so I end up with pair C. If the previous one was for B, and the previous to that was A. So A is the Fourier series pair on a unit interval. B is the Fourier series pair, transform pair, on an interval of length t. C is the Fourier integral pair of an interval that no longer is in play because it's really the whole real line. You get here to C from B, and no longer do you have to fit standing waves inside a closed interval, which means that they inherently discretize, leading to discrete frequencies, but any and all frequency go on the continuous frequency axis, and so you have the continuous time, continuous frequency, with f as a continuous variable rather than a set of index frequencies. So that is the Fourier integral transform. And all of that holds as long as S, the signal under consideration, lives in L2, is square integrable, but over 0, 1, 0 to 2, infinity to infinity. So maybe this picture here is for a phi, and we're really talking 0 to 1. Here we begin by talking to something that's 0 to t, or negative half to plus half. We can also talk about how to extend these things, and so on, periodization, but I'm not going to do that for the moment. It's no longer that relevant. I've made my argument that on a length 1 interval, we had A, on a length t interval, we had B, and on the real line, t going from negative infinity to plus infinity, we have C. And if we thought about frequencies here, in A, they were just the numbers, 1, 2, 3, 4, 5, 6. In B, they were 1 over t, 2 over t, 3 over t, but they're discrete points. And in C, there is a frequency axis that is continuous. That also goes from negative infinity to plus infinity. Whereas in A and B, the frequencies are points. Here is M, and then out of space. And here would have been M over T. Okay, so these two pictures go with A, these two pictures go with B, and these two axes go with C. Let that sink in while I bubble this up a little bit. All right. Okay, 63. I'm now going to do something that you all do when you're dealing with continuous anything and you're computing it, you're discretizing it. Now I'm going to give you Fourier integrals and sums. I'll just call it the Fourier transform at this point. And I want to discretize time. And I'm about to tell you that of course, doesn't change the frequency from being continuous, but it does something to the frequency that is very important. Okay, so where's my picture? Here is time. Now time is discretized. So I'm actually going to call time index times delta t, and delta t would be the sampling interval. And maybe I'll change my mind on this notation, but that's what I had. Now time is an index, the first, the second, the third. Okay, so that's called sampling. And whoever brought up Dirac's delta last time, this amounts to a multiplication by a shifted Dirac delta, but I don't really even need to talk about that. I say, well, look, I'm not talking about this. This was a continuous time variable. This is a discrete time variable, rendering this an index, a counter, and that an interval. So now I'm going to attempt to write, also starting from the back. Should I do that this way? Yeah, I'm going to start from the back, okay, just so that the transform is always below here, but I'll leave some space. I'll say, well, what is that going to do? I mean, I've done something, so I'm going to give it a little index to show I've done something, P for particular. And I'm going to try and write the Fourier transform, what you don't see is I'm just looking at C. Maybe I'll leave it here. Right? I've been sampling, that's all I'm doing. And now I'm going to try and copy what I might have just done by sampling. And I know it can't be an integral anymore, right? Because I've sampled, so it must go to a sum, that's for sure. And my t is an index now. So far, so good. And I've turned my s of t and an s of t times delta t. All right. My e to the negative I type I 2 pi unchanged. My frequency, I'll still want to know it, so I'm leaving it. My time goes to t delta t. So far, so good. And my integration interval better be in there, so I'll call delta t out at the back. All right, that's clearly the equivalent of C for this new situation. Why do I call it S of P? Well, here's what we can notice. We notice that when we do it, and it doesn't take much to verify, that if you take S wiggle P of F and you're adding to it some integer times 1 over delta t, then really what you should do at home is to say, okay, well, what does that mean? So you replace f by f plus n delta t, but it's the exponential of the sum, so that's a product of exponentials, and you pull out the product of what you've just done, and you realize that actually that was 1. And then that shows you that it turns out that this thing is equal to what you started with, okay? So starting from the continuous time, continuous frequency transform pair, which was all C, I sampled in the time domain. I looked at the implication by writing what it surely ought to be, knowing that it could be, it needs to have some other effects. And then I noticed that, aha, turns out that whatever this is, this sum, if I have this variable f, that whatever it does after a certain while, all those values repeat. That's the first realization here, that sampling in time periodizes in frequency. Okay, that's what it is. So now I'm going to attempt to write what the time version of this is. And again, I'm going to get my inspiration from C here, and I'll see S of t. I'm going to replace it by t delta t. I'm going to want to stick in S of p. I'm just going to write it to see that you will see that it kind of makes sense, but I need to do slightly more work to make full sense of it. And when it makes full sense, it makes a lot of sense. So my inspiration is C. It now turns to D, a whole different transform pair. And I write S of the discretized variable, now t delta t. I still have continuous frequency, so I'm going to be integrating. But remember, I called it pi, p, or whatever. Notice that this is trickery because, I know it's going to happen, so I predicted it. And it's not entirely ingenious here. It's a bit disingenuous, in fact, to know the answer going in. But here it is, right? So I do S of p, the Fourier transform of this frequency. And I'll be just writing e to the I2 pi. And I repeat my f that I want to know about. And I repeat my time, but now it becomes t delta time. And I have an integration interval df. And now I'm going to do another trick that I am going to justify in the second after. I need to figure out what the integration intervals are. And I'm going to begin by giving you the answer and say, well, this needs to be 1 over 2 delta t and 1 over 2 delta t. And then I could say, well, every pair of them, if you're like, what does that have to be? I know the answer, I'm giving it to you. But remember that every pair is, to be justified, has been, but if you're not by this all-important orthogonality, right? If you're unsure what it needs to be, you can just say, all right, let's start from that. Let's integrate on both sides. Let's take the thing, let's do the, and then you end up with finding that that indeed is an acceptable answer. So always return to orthogonality and orthonormality to help you out if you're unsure about the pairing, okay? So I made the periodic point about the frequency version. And now I'm going to make a point and wonder why these limits have changed in what they should be. And I'm already saying that they have changed, but now I give you an interpretation, not a justification, because that's in orthogonality, but an interpretation, which is the most important thing. What up at the limits? With, is that how you spell it? No. Okay, so I'm coming to what I think is a very important point about any and all of this. Okay, so I want you to look at D1, right? ST delta T. I want you to see that these limits integrate that SP variable, and then you want to compare that to the pair C, the transform pair C, and you're like, well, that was integrated over the whole thing, but of course the argument was different, right? Never forget what you are integrating, right? So what are we doing? Correlating, integrating, cross multiplication, integrating against, it had this here, S wiggle, and the limits were negative infinity plus infinity, all frequencies forever. Now I'm already noticing these frequencies are periodic, and I'm integrating with new limits, but there's also, of course, a new function. The pair is incontrovertible because of orthogonality, but I now need to interpret what has happened. What is the difference between S of t with these limits and that transform, and S of t delta t with these new limits and that new thing? I need to understand that, and that's going to happen in the next 7 minutes. So that's my objective, 64. Compare S of t under this Fourier transform pair. That was the continuous time, continuous frequency case, which you're all often learning in school anyways, because it's the easiest one. Everything. Discretization is, as you will see, not without its effects, so people don't talk about it until they're doing real work, which we are doing. We have E delta t under this discrete time continuous frequency. In other words, what is the relation between S of f wiggle and S sub p of f, about which I already know that this was periodic? Not. So here is the derivation, which is just 2 lines, and maybe I'll just write the result. We start from st delta t, and we're saying, all right, let's just write it. Okay. Instead of writing the full integral, pretend I'm rewriting the whole thing. I start from negative plus infinity, blah, 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 the same thing as before. I'm going to actually say, let me integrate this. I'll write a little more. I'll do the details later. There's one trick. It's just, I don't normally like to spend time in the math, but this is one of those things then you'll read it elsewhere, and then you want to really see it's not that hard. So you split this integral into pieces, and I'm going into pieces like this between some made up things here, 2n minus 1 and 2n plus 1. So let's n be 0, and then it's from negative 1/2 to plus half. So we've had it before, and now I'm sectioning this integral into portions of the continuous frequency axis, apparently for convenience. And I do my integral in pieces like this, and then on to the next one, and then on to the next one. And I guarantee I do all of them by letting n be going from negative to plus infinity. And then I write again S of f and the rest. If I have time, I'll fill it out here, but blah, 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 e to the I pi and so on, nothing changes. And then I make a change of variables. And I say, well, that turns out to be the same sum, but I return to 1/2 delta t and 1/2 delta t, but I change variables such that my integration function S wiggle is really S of f plus that interval. You'd have to verify that at home, that I change f prime, if you will, to f plus n delta t. In fact, I do prefer to write it as primes here so that nobody gets confused. E to the I and so on. As well. If this is unchanged, I'm going to fill this out later so you have it. And then I'm going to switch the integral and the sum. And then, of course, I'm noticing that this guy was already special, right? And then I'll write the result. And the result is this, that S of t delta t, the sampled time function, is this integral from 1 over half to plus over half of something I've just literally made to show you that it contains an infinite sum of contributions of the S wiggle function at these frequencies plus n delta t. I'll write the whole thing for now, for once, I have 2 minutes, times e to the I 2 pi, frequency, nothing changed, t delta t df as before. Those integration variables really all should be red. That doesn't matter. Okay. And so I compare that with what I previously wrote as d, right? So first I had d, I'm like, you know, I'm just doing it, but it was S wiggle of p. And now I'm asking, how does that relate to the S wiggle that I know is the continuous version of it? And that shows you right here and right there that this is S of p, S wiggle p of f. So what thereby are we saying? We are saying the following, and this is very important, and that will be the good start for next lecture. We are saying two things. First of all, so now we know what S wiggle of p is. We knew it was periodic, but what do we really know about it? We know that it contains the true contributions to the frequencies f of the signal that we're analyzing within the limits of 1 over 2 delta t, and then contaminated by all the stuff that is outside of that target interval, negative half t plus half delta t, which have no business being there, which are literally contamination. And so the words here, and then I'll draw some pictures later, are that the Fourier transform, the spectrum, if you will, even though I don't like to use the word now, the S hat PF is related to S hat of F, which I want to know, but it is contaminated. It is also known as aliased. It's an aliased, contaminated version of the truth, which we wanted to know. We knew it was different. We knew it would periodize, but we didn't just know exactly what the relation was until now. So this tells you if you have a continuous signal and you time sample it, and then you inquire about its Fourier transform to figure out what frequencies are at play, that you're getting the result only within a certain bandwidth, and that the values you get are not the real values, but they receive contributions of the portion of the spectrum from the true signal that were outside that bandwidth. And that's what we're going to draw some pictures and some more intuition about what that really means is happening. But you heard this here first. This is called alias. And that means by implication that whoever samples anything, which is all of you all the time, and whoever wants to know about cycles like eccentricity, periodicity, obliquity, whatever, that you have to have an understanding of how your frequency contributions are seen through the lens of your sampling, how much you can see, how far you can see, and then how to optimize it to learn something. And everyone will have familiarity with the bad effects of aliasing because, you know, I'll show it in pictures. But here we have the beginnings of an understanding of why it happens, and then we'll talk about what to do with it all. So ABCD, D remains the discrete time continuous frequency transform, but we have now learned that the first line of D relates, so I'll call it D prime, how SP relates to the S, knowing that S is the one that we really want because we assume that this thing exists and we want to know it, but we can only sample it.